To derive then the equation that these r's obey, we want to begin with the fully general equation without any restrictions. So let's begin then with the full three-dimensional time-independent Schrodinger equation, which we know how to write down, right? It's the energy times my full three-dimensional wave function, psi of r theta phi. And I know that I will get the energy times my wave function if I apply my Hamiltonian to that wave function. And at this point, I'm going to build in then my expansion in terms of these functions r. But I'd like for you to notice at this point that I'm not making any underlying assumptions. I'm guaranteed that I can have some kind of an expansion along these lines. Next, to make progress, I want to see what my Hamiltonian does when it acts on this sum. And of course, as we know, we can always move the Hamiltonian into the sum. It's a linear operator. And my job now is to apply my Hamiltonian operator onto a product of two functions in this form. Now, the Hamiltonian operator itself, as we had written up above, is a sum of three individual terms. So we're going to take these three individual terms one at a time. So the first task is to write down the application of this piece on the product r times L. Now when I do that, I want you to notice that because of this nice separation among the variables, right, these operators on r, especially this derivative, as far as this partial derivative with respect to r is concerned, y is just a constant. So when I apply this operator to this product, I can just pull the y all the way out. So let's pull that out and write it then at the beginning of the line here. So I'll have YLM theta phi multiplying then, I've pulled that one out, multiplying then, what remains is this operator is operating on the capital R, and that would just give me then minus h bar squared on twice m, 1 over little r, second derivative of r times big R Lm of r, like so. And I've already included the y piece. I've factored that out. So that's the first part. Now let's look at the second part. The second part now, I have to apply this operator on my product, and this works very nicely in kind of exactly the same way, but opposite. The point is that the L squared operator, as we can see, depends really only on the angles. Consequently, when I apply this L squared operator to this product, I can pull, not the y's because they depend on the angles, but I can pull through the r because it does not depend on the angles. So let's just set the r aside for a moment. We'll put it in our memory bank. We'll pull it back in just a moment. And let's focus next on what happens when the L squared multiplies my YLM. Well, that we know. That was the whole point of the preceding lecture. When L squared hits y, what I get back is just y back again times this constant a. So that's why I included this parentheses. So for my second term, I've already written down the fact I've got my y back again. I then have plus, and what we learned is times y, we get our value of a, and the allowed values of a have an L times L plus 1 times h bar squared. So I've taken care of then the L squared part of this acting on my y. What remains then, after I apply the L squared on the y, is I also then have to multiply by 1 over 2mr squared. So let's get that in there. So there's divide by 2mr squared. And then finally there's the r piece that we had pulled through our operator and put off to the side, which I had better put back now. So then that will become times r Lm of r. Oh boy, we're getting there. One last term to go. Fortunately, the last term in the Hamiltonian is just multiplication by the Coulomb potential. So when that multiplies the product that I'm applying to, I've already pulled out the y, so I just have to include another term which has my Coulomb piece, z Coulomb's constant e squared over r, and now it's just multiplying. I've factored out the y, it also has to multiply the r sub Lm of r. Now, it's worth stepping back just a bit. When we look at this, what I hope you can see is that what I have in here is starting to look a whole lot like a Schrodinger equation. I've got a function and some potential. I've got second derivatives. There are some other confusing pieces. But this radial components look a lot like some kind of radial Schrodinger equation. And what I'd like to do is to separate them out from the fact that they are multiplied by all of these YLMs. But we have a precise procedure actually for doing that. Right? Whenever I have a sum of YLMs times some arbitrary function of R, which depends on L and M perhaps, right? But it's a function of R, that's precisely the mathematical form that I have up here for any general function. And for a general function, if I want to extract the parts that depend on the radius, I have a procedure for doing that. I just apply the Hermitian inner product to both sides. So what we're going to do now to the above equation is we're going to apply then, we're going to take the Hermitian inner product of YLM, and I'm going to do that on both sides of my equation. And I'm going to make one other little adjustment, so leave a little blank space for the little adjustment. And if we do that, we will get the following result. When the YLM inner product comes and hits my left-hand side, E is just a constant. I can always pull that out of my inner product. And at that point, what I will be left with is actually the YLM applied to the wave function psi. So when I apply the YLM to my wave function psi, that just picks out the function RLM. So left-hand side is E RLM of R. On the right-hand side, as we've discussed, and that's why we're doing this, applying it to a general function just pulls out the constants multiplying the YLM. So I will just get these remaining pieces of the equation. So that will then have a minus h bar squared on twice m, a 1 over r d squared dr of r times cap r Lm of r. And at this point, by the way, I want to remind you, or remind myself actually, we should leave a little bit of space between the E and the R, which has to do with the second thing that I'm going to do in my equation. Now, next, I have my remaining terms here. So there was plus L times L plus 1 h bar squared over twice mr squared, multiplying r, and again leave a little space. There's an r Lm of r. And then finally minus the Coulomb parts, z Coulomb's constant e squared over r. Let's leave a little bit of space, and then r sub Lm of r. Now, this equation definitely looks like the time-independent Schrodinger equation. Energy times r has all of my operators in here. There are only two little pieces that are giving us a little bit of trouble. And that is that I've got an r inside my second derivative, a little r, and I've got a little r outside my second derivative. But I can handle that quite easily, right? Let's multiply both sides by r. If I do that, then I'll have e r times big R. This r will cancel. I've got r times big R in there. That's interesting. I will get another r times big R here and another r times big R there. And the reason why this looks so nice is, notice I can put some parentheses around r times big R. Here I already have that combination, r times big R and times r times big R. And now, in terms of the function r times big R, this looks exactly like the one-dimensional Schrodinger equation. It's got a second derivative of my function, plus then some function of r, right? Some effectively like a potential times my function. So to really draw that analogy out, I'm going to finally define a special combination here. I'm going to define rho sub Lm of r as r times capital R Lm of r. And then once we know how to solve for this rho, it'll be easy then to recover capital R Lm of r, right? It will just be rho Lm of r divided by r. So, with that definition then made, let's write down then the equation that rho obeys. It obeys this effective Schrodinger equation. So we'll give it its name. This is the effective one-dimensional Schrodinger equation. And it looks as follows. I'll write it in our usual order. We'll put this term on the other side of the equation. So what it has is minus h bar squared on 2m times two derivatives with respect to r of, now this combination is just rho Lm of r. And that looks just like kinetic energy operator acting on some wave function. Plus then, I have a sum now of two terms that are multiplying my rho. So I'm going to gather them together because they seem to act somewhat like a potential term. The first term is L plus 1 h bar squared on twice mr squared. That's multiplying this combination, which is rho sub Lm of r. Oh, wait. Actually, I wanted to factor out the rho. So then I have minus the second piece, the Coulomb piece, Coulomb's constant, times z e squared over r, and all of that multiplies rho Lm of r. That's one side of my equation from over here, and the other side then is just, again, this combination is rho times rho Lm of r. Oh, times the energy. I've got myself here a little jammed up. Excuse me for this, but I want to really make it fit on one line here. So that's rho Lm of r equals my energy back again times rho Lm of r. And we can put a box around this and these definitions because this is what we really want to focus our efforts on learning how to solve.